Hello YouTube! What you just saw is a test bar I've just turned. This is the final step in my latest effort of trying to get this lathe closer to a LikeFactoryMade state or even better. The closer these two diameters match, the closer we are to perfection. But trust me, trying to squeeze perfection from a 32 years old machine wasn't an easy task. When I got this machine, I was hoping initially to be more like a project kind of type, where I just throw the old controller, put a new one. It was already 30 years old. So I thought I would just get away with putting a Linux CNC on top of it and call it a day. Oh boy, it was so much more than that. There was just too much play, too much wear. Some of the oiling lines have failed, and that has caused serious damage to the lathe bed. I had to send it out for a regrind. But once that was done, every single surface had to be readjusted to fit again. A long process involving both hand scraping and even power scraping. Even with a perfectly reground bed, the team who did the headstock alignment made some serious mistakes. And that's what we're going to tackle in this video. So, buckle up. This journey took about 6 months with plenty of ups and downs. This video is a 2-part series, so if you don't want to miss the next part, please subscribe, hit the notification bell, so that you don't miss the part where I actually do the measurements of these two diameters and see what we've done. But until then, let's begin. We'll start by removing the sheet metal covers of the headstock. Something is still holding the front cover. The way cover is blocking the access to a screw, so it needs to come off. And now that I need to remove the lid of the gearbox, I'm about to realize the mistake that I previously made. The old gasket was damaged, so I thought I would just use some silicone gasket, but bad idea. Bad idea. It seems that I just keep finding new and new forms of captivus. I don't have the footage of finally releasing it, but if others have made the same mistake, I can give you a hint. I screwed a custom-made eye bolt where the oil plug of the gearbox is, and then pulled it upward with a chain hoist. Being the first time I removed the spindle of this lathe, I was a bit anxious not to mess something up. So far, I had the good spindle run out, and I want to make sure it stays the same. I can only imagine, yet, the cost of some spindle bearings, so I need to handle them with respect. With the lid and the retaining nuts being removed, I could finally proceed with pulling out the spindle. Luckily, I had all the needed tools, so I could entirely avoid hammering the spindle bearings. It was a 4-hands operation, but we've managed to extract it safely. But while the spindle was almost out, I got some bad news about the bearings. It seems that 30 years of life have left some wrinkles. And it seems that Botox for bearings is not invented yet. We'll figure out the bearings later. Now, let me show you how well the headstock sits on the V-ways after I removed the screws that were holding it down. Precision work, isn't it? No wonder I was turning unwanted tapers. I'm gonna flip this down so that I can show you what the problem is. See this green thing? This is turkite. It's perfect for sliding surfaces because it has a low coefficient of friction. But this is not a sliding surface. Why do we have it here? Well, it's a combination of bad design from a factory perspective plus the stupidity of the company who did the regrind and geometry rebuild attempt. I think it's bad design because having the headstock sitting on the V-ways makes it completely unadjustable. But once the factory adjusted it correctly, they inserted an epoxy filler between the headstock and the bed so that they become like a single piece. When the bed regrind was done, that epoxy fell off, so they filled that space with something. Given the bad design that I cannot change, I will go with the same approach as the factory did. So I stripped out the useless turkite to make room for the epoxy filler. And now, look what play we have. I could almost turn on Morse taper just by tilting the headstock. After everything is aligned, I will inject some epoxy into this gap and that will secure it in place forever. Maybe it's just my commitment issues, but this forever seems kinda scary to me. But until that point, I need some means to handle the headstock, as it weighs more than my girlfriend does. This sheet metal allows me to quickly have access underneath of it when I need to switch between hand scraping and testing. And with the right friends, I got my hands on it just a day later. Now that I have all the setup, you might think that I would just pop a test bar, align the headstock and inject the epoxy, but I can't. When they tried aligning it, they realized that the factory Morse Taper 5 does not match their test bar. Instead of checking their test bar, they reground my taper to a wrong angle. Now the test bar has play, so I need to send the spindle and the test bar out for a regrind to fix their mistake. The new team said it's an easy fix. You'll see how easy it was a bit later. With about 3 weeks of waiting ahead, while waiting for the spindle to get back, I decided to tackle other improvements that I wanted to make, and for that, I needed to fully dismantle the cross slide. Fully dismantling the cross slide isn't quite an easy task, but I've done it so many times before that I already know what annoys me and how I would design this differently. In the last years I had several rebuild stages. Each of them got me closer and closer to where I am now. After each stage, before what I knew, I discovered what else I would need to fix or improve. As you may have seen in another video, after the top cross slide was reground, in order to keep the ball screw aligned with the saddle, I had to plate with turkite the bottom of the X-axis slide. That's in case you were wondering what's that green stuff that you see over there. As you will see in a minute, the cable management is a pain, but I have a plan for that. Imagine that before I switched to Delta servos, the old 30 years old ones were even beefier, so everything was more crowded. Now that we safely got the motor out, we can finally remove the latest sheet metal parts around it. And now, let me show you what a beautiful cable nest we have inside the apron. These two hand wheels have an incremental encoder on the back, feeding 100 pulses per revolution into Linux CNC Mesa board. You didn't see the cable nest yet? Just a second. There it is. Each time I need to work in here, I regret I did not went with EtherCAT. Instead of a bunch of cables going into the back cabinet of the machine, I could have just used an Ethernet cable and a 24-volt power one. But at the time I started this retrofit, there were not so many videos with Linux CNC EtherCAT on YouTube, and I did not want it to be the first one complaining that I cannot make it work. Also, the cost of the encoder slices was at least prohibitive, and I needed 3 of them in total. With the electrical panel being disconnected, now I can finally release the lube lines. In case you're not familiar with this system, each line is connected to a meter valve, so that each lubricating point gets a predefined amount of oil. I upgraded the ones for the front and back ways with some bigger ones so that those points get more oil. Just a quick disconnect of the Z-Limit home switch and we're ready to pull out all the cables. Now, here is where the current design gets very annoying. If I want to inspect the V-ways of the saddle, or check from time to time if the oiling is working correctly, or if I want to check the thrust bearing of the ball screw, I need to pull out all these cables to be able to do that. These cannot remain like that. It's an awful design. An idea that I have in mind is to create a custom cable duct that goes under the lathe bed and connects the apron with the back portion where the motor is mounted. As for the empty space that remains here, trust me, I have a plan. One that will scratch my precision itch. After jumping through all these hoops, I was finally able to remove the piece that holds the X-axis ball screw. You might wonder, why am I trying to tear this apart? Well, after 30 years of use, I have a bit of backlash and the ball nut feels a bit crunchy. I was considering for a while replacing the ball screw, but before I ask for a quote, I need to come up with a drawing. The manual does not have any details drawing of the ball screw, so I need to take them out to measure them. The last time I tried, I could not remove the key, so now I'm trying my luck again. It seems that my Knipex pliers are not convincing enough, so time for plan B. I was hoping that heating it locally with an oxypropane torch will do the job, but it's more stubborn than I anticipated. Luckily, I have a plan C too. I've seen this a few times on YouTube but never tried it. I think adding a weld bead on the key will do the trick. Oh yes, thank you YouTube. It's you who gets the credit for this. What I liked in other assemblies was when the key had a threaded hole for a screw to push it out. But for this 4mm key, it's too thin for that, so I'll need a different solution. Time to get out the angular contact bearings. They have some kind of sheet metal caps on the ends that protects them from the debris. The shaft was still hot to the touch and the bearings won't come out. It seems that they are not coming out due to some burrs or dents or something. Believe me or not, it hit me just now while editing that the section closer to the keyway that got heated dilated, so that's why the bearings were not coming out. Off camera, they did come out. So I split the double ball nut and with some brake cleaner I'm trying to see what makes it feel so crunchy. Based on how it feels, we'll most likely end up replacing this, but I was curious what's inside after 30 years of use. I've put a napkin below so that I can collect everything that comes out. And oh boy, it did came out a lot. Remember that precision itch I mentioned? Well, you know what's cooler than a closed loop motion control? A full closed loop motion control. Because why stop halfway when you can go full nerd? So I thought, hey, let's slap some half micron linear scales on it and really commit. Sure, a preloaded ball screw sounds fancy, but even without backlash, it still slides to you over long distances. Add some bells between the servo and the screw and now it's a game of guess the position. And don't forget about the stick slip effect on the ways, because machines love drama. That's where linear scales come in. They cut through all the nonsense and tell you where you actually are. While I was busy with this side project, another long postponed one started creeping up on the horizon. Last year I had a small flood after a heavy rain, but since it was the first time in the 7 years, I figured out it was just a fluke. Well, it wasn't, and this time it came back with a vengeance. So I finally did something about it. This 5-inch threshold should give me a decent level of protection going forward. Okay, back in business. I've modeled a rough version of the apron and saddle assembly in Fusion, and from there I can design the cable duct and other sheet metal upgrades needed to fit the linear scales. In the current approach, the sheet metal that holds the cable duct leaves no room for mounting the linear scale. But with a more compact servo motor, I was able to design a shorter version that leaves extra space for the linear scale. With the entire saddle and apron assembly, it's time to see if CAD matches reality. Thanks to my friend Horia, I got all the sheet metal parts in record time. Thank you for supporting me in this journey. In order to make that entire assembly more efficient, I welded some 8mm nuts that will hold the screws of the cable duct. And it seems that my measurements on which I've made the CAD were accurate enough, so everything fits as intended. Time to put a hole where the red section is, so yep, it's milling time. Initially, I was wondering how to hold this apron for the milling operation. Then, it crossed my mind how simple the problem was. By keeping it attached to the entire assembly, the clamping became trivial. I was too lazy to model this pocket infusion, and my controller doesn't even have basic conversational programming yet. So I ended up doing manual milling on the CNC. Honestly, it probably took longer this way. But hey, the hole for the cables is finally there. As I mentioned in the beginning, this video was not scripted, so for some of the milestones I just have pictures to show. The cable duct changes came out like I expected, and now the wires are coming from under the lathe bed. Also, the linear scales integrate perfectly. But I realized just when I was trying to mount it, that I needed the hole to be able to connect the reading head of the linear scale. But an engineer's life gets easier when you have a mill at your disposal. As for the x-axis, here is the plan. I'll use the space freed up by relocating the cable duct to mount the linear scale. Then another stainless sheet metal cover will go over the scale and the end of x-axis to keep everything protected. But you'll see more about the final version in the end when I'll put it all together. When I got the bed back from the regrinding, they included a test report showing that it was flat. And on paper it looks good. But I don't trust them anymore, so I wanted to verify myself. It's not yet epoxy to the base, but I've aligned it properly, and now it's time to see how flat it actually is. I have a shim stock that's just 100 of a millimeter thick, which is a quarter of a thickness of a human hair. By moving the shim stock at the ends of the straight edge, I can check the pivot point. If the pivot point changes to where the shim stock is inserted, it means that the height difference between the old hinge point and the new hinge point is less than 100 of a millimeter, so less than a quarter of a human hair. And in this case, it seems that the waves are flat within less than 100 of a millimeter on the usable length of the bed, which means I can confidently move forward with epoxying it to the substructure. For this rebuild, I was racing against the epoxy's expiration date in August 2024. And by the time I actually poured it, it was already September. The gaps between the bed and the substructure will be filled with epoxy, and then I'll level the bed again before it sets up. With only a 15-minute window from mixing the epoxy, I was in a race against time to pour it and level the bed as precisely as possible. So, no footage from that part. I did not have the mental bandwidth or physical space to squeeze in a second person and a gantry without camera getting in the way. Throughout the leveling process, I moved the slide back and forth in roughly 150mm increments, giving the bubble about 5 minutes time to settle before taking each reading. The resolution of this level is 200 of a millimeter per meter per division. So applying that on the weight of the bed, we have a resolution of 4 microns per division. Here are some measurements that I recorded. The first and the last reading are the same, and the middle ones are offset by a half of division. So with 2 microns twist, I can declare myself satisfied. Now that the bed is epoxied and leveled, Spindle came back from regrinding just in time, and new bearings have arrived too. So we can finally get back to the main storyline of this video. For now, I'll take off the hinge so that I make room for installing the internals of the headstock. With just 2 gears, the gear headstock design is quite simple, even though it looks kind of intimidating when all the parts are scattered on the table. Since I'm already at this stage, I'm replacing all the bearings with new ones, especially since the standard ones are pretty cheap. To avoid hammering them in, I'm using the air fryer to heat them just enough. Set it to around 100 degrees C, and after a few minutes they're good to go. I rushed removing the old key, so I am replacing it with a new one that has a threaded hole. Also, the old one was a bit loose, so now it's a perfect fit. I think from here the assembly is kinda self-explanatory, so I'll shut up and let you enjoy the process. Now that we have the arbors pre-assembled, we can start putting them in. I'll do first a simulation to figure out the mounting order of the bearings, then take them out and install the bearings on the ends. Since this will run in an oil bath, I decided to remove the plastic protection from them. The first arbor has 2 small bearings on one end and a much larger one on the other end, but only the small ones can be installed at this moment. For the second arbor, both ends have bearings of the same dimensions. Don't forget the washer, Vasi. The washer! The washer!
Fuck!
I hate that I need to use the extractor on the new bearings. And that I'm bumping around precision ground gears. This time I added the washer.
Intro!
But the bearing cooled too fast, so I had to extract it once again. While I'm heating it up some more, I decided to minimize the risk of this happening again with a bigger bearing. And that one entered easily. Now, the third attempt for this one. This time, I was lucky. Now we can add the preloading spring washers and the caps for the end of the arbors. This is the last shaft that needs to go in. It has O-rings in the end, so we'll replace those to make sure we don't have any oil leaks. This bolt detent with a spring will keep the changing fork in one of the 2 stable positions. Here I also replaced the key with a threaded one, and the Knipex pliers are just the perfect tool to press it in. We're almost ready to give it a spin. The gears are shifting fine, so off camera I mounted the reground spindle. When I've sent the spindle for the regrind, the play at the end of the test bar was 0.2 mm, but that was barely noticeable. Now it seems more than that. I've cleaned both cones and made sure there are no dents, but no matter how much I test, it's worse than before. I tried blowing it up and see where it makes contact, but my blue is so faint that I can barely see it. So, let's see what the dial indicator says. Yeah, we went from 0.2 mm to 1.5 mm. Just 8 times worse than before. One thing was clear. I needed to pull it out again and find someone else to do it again. The problem is that with each regrind, the face of the cone becomes larger and larger, and the cone goes deeper into the spindle. After a useless talk on the phone with the guy who supervised the regrinding, where he did the best to convince me that he did everything right, I decided to get some real measurements of the taper angle. So I took it to a friend that had a coordinate measuring machine, and the results were shocking to me. Here is the measurement report. This is the target angle, and this is the measured angle. That's quite a difference. You need a special talent for that. A month later, I found a company who let me supervise the process, so I brought my micron dial indicators and made sure everything is perfect before they begin. Yet again, I found another lazy and disinterested operator, but this time I was willing to fight with him if needed. This time it was my way or no way. And since the spindle taper got deeper, we had to grind a few threads from the test bar. After almost 8 hours of me making the operator curse his days, we had no more room for other mistakes, so I had to call it good enough. With about 40 microns run out and less 10 microns play, I decided not to risk anymore. There is another thing that bugs me that I cannot accept. The company who did the regrind wanted to have a pivot pin to help aligning the headstock. And here is how straight they've drilled it. In my world this is unacceptable, so I made a jig that gets bolted like the headstock would, and then I plunge with an end mill clamped in a cordless drill. It's far from the ideal setup, but I've managed to enlarge the already existing hole and at least make it perpendicular to the plane it was made. The hole for this pin was drilled through the headstock, so that one too needs to be corrected. I'm enlarging it on the mill and I'll make a plug for it, but at least now it will be centered and perpendicular. Just another finishing pass. Up to this point, all the tests were done using the old bearings, but now that I've seen the regrind results for myself, I am confident enough to install the new ones. I laser cut some discs to pull out the old bearings and press in the new ones. Luckily, my friend Victor is helping out. 2 engineering brains are always better than 1. And yeah, these do look kinda tired. After ensuring that the bearing seats are perfectly clean, we can proceed with installing the new ones. Oh, you have no idea how nervous I am handling these precious bearings. You know what this paper says? That if I drop one, I need a new set. Starting with the front spindle bearing, so let's get it warmed up. While it heats, I'm stoning the spindle back face and the dust labyrinth to clear any burrs. With a 70mm bore and a long shaft to slide over, I played it safe and pulled the shaft too. And yes, it paid off. Being a matched bearing set, for the highest precision, the outer races have a mark that needs to be aligned. I'm drawing a line on both bores at the same place, so we'll use that to align them. I also noticed that the old one came off a bit too easy, and they were shifted, so I decided to add a bit of Loctite 243 to prevent that from happening again. We debated about this, whether it's a good idea or not, but the curing time is quite long, so we were hoping to preload the bearings before it sets up. It feels like the rear bearing slides in even easier, so a bit of Loctite will help with this. I said a bit of Loctite. Now that's better. With another pair of skilled hands, mounting the spindle went way faster than I anticipated. We easily fit within 10 minutes curing time of the Loctite 243. After so many times we took the spindle out and put it back in, I really hope this is the final assembly. Now hoping that the rear bearing doesn't cool down too fast. These kinds of bearings are a bit tricky to preload. According to the factory, I should tighten the bearings until there is no axial play, then run the machine half an hour at half the nominal speed and measure the temperature of the bearings. If the preloading is right, the temperature should be below 50 degrees Celsius. But in order to know when we're at half the nominal speed, we first need to mount the encoder pulley. With the current preload, the spindle runout is about 2 microns, but I'm quite convinced we can do better than that. Okay, so if for the correct spindle preload we need to run the spindle for half an hour, it means we need to add the oil. Seeing the wear on the old bearings made me wonder if the oiling was working correctly. To make sure I protect my investment, I decided to cut a plexiglass lid and see how the oiling works at different speed ranges. I am now using ISO 32 oil, which is exactly what the manufacturer recommends. The level of oil is correct, but the results are disappointing. I also try higher speeds, but I'm not very comfortable running the bearings without any lubrication. So I decided to help a bit. After playing with the speeds, I've managed to get a speed where the oil dripping works, but this method isn't reliable. This cannot remain like this. It's definitely a major flaw. With much effort, we've managed to get the preloading just right, without exceeding the max temperature of the bearings, and without starving the bearings of oil. We've come a long way, we are almost there, but the spindle lubrication can't remain like this. Therefore, in the next video, we'll get the headstock off and work on a proper lubrication system. Also, we'll continue the journey with leveling and aligning the headstock. Then, put it back all together and do some calibration test cuts. If you enjoyed this video and you don't want to miss the next episode, please subscribe and hit the notification bell. Thank you for watching, see you next time.